Greetings, students. So, in today's lecture, we are continuing with your Unit 2. Okay. So, in Unit 2, we have started with your transformer. So, transformer construction we have seen, and the classification of different types of transformer also we have covered. And in today's session, what we'll be dealing is we'll be dealing with your EMF equation of the transformer. So, it is a derivative part, okay, but it's a very important question. So this EMF equation we will be involving. Also, we will be dealing some problems. I think one example problem is covered with respect to this EMF equation in today's lecture, followed by the phasor diagram. So already I have told you about somewhat a brief introduction to the phasor diagram I have already given. So with respect to that, we will be continuing the phasor diagram when your transformer is at no load condition. Okay. Next is that the phasor diagram when the transformer is connected with the load. Okay. So already I have said the load might be of three types. Okay. Resistive, inductive, followed by capacitive. So if it is resistive means you will be having unity power factor. If it is inductive means you will be having lagging power factor. If it is leading means you will be having as a capacitor as a load. Okay. So we will be seeing these things in today's lecture, and this is what your agenda will be. So first we will be starting with the EMF equation. Okay, we will be starting with the EMF equation. So as I said, it is the derivative part. So you already know about transformer, right? So this is what we have covered. I will be giving a small brief intro again. So here we will be having primary. So this is, corresponds to a primary, and this side corresponds to your secondary. So based upon the bindings, okay, based upon these bindings, okay, you can tell that you can step up or you can step down the voltage. So that is what the main function of your transformer. Okay. So now we are going to find the EMF equation. EMF equation in the sense the output equation, okay, the output voltage equation of the transformer we will be dealing today. Okay. So starting with the EMF equation. So this is that's a PDF I have attached also. Okay. So this is the EMF equation. So here you can see. So this V1 side, this V1 is your primary supply voltage. Okay, it is the primary supply voltage, and this V2 is your terminal voltage. Okay, so this is will be corresponding to your primary, and this will be corresponding to your secondary. Okay, so now after that the same things is the, so this E1 is nothing but the induced EMF. Okay, so will be finding for your equation for your E1 and E2. Okay, so this E1 it is easy to describe because it is at the primary side. So primary side voltage is what we will be supplying. Okay, so here capital A refers to the area of the core. So area of the core, we have already seen about the core. So the entire windings will be wound in your core. Okay, so it will be wind across like this. So A is nothing but the entire area of your core. Okay, so next F is the frequency of AC supply. So in our household we'll be using 50 hertz supply. Okay, so in the household we will be using 50 hertz supply. Okay, and so here BM. So this BM refers to the flux density, and the unit of this BM is Weber per meter square. So BM is nothing but the flux density at this core. Okay, BM is the flux density with respect to this core. Okay, so phi m refers to the maximum value of flux. We have already seen about your flux linkage. Okay, we have already seen about the flux linkage. I have told about flux linkage. So your phi m will be corresponding to that flux linkage. Okay. So now moving on to this diagram, we'll be seeing about this diagram. Okay. So here, this is a flux. Okay, flux they have given. So flux for a particular for one period of cycle. So here the t will be for 1 by 50. Okay, so which is nothing but 1 by f. Okay, so at the quarter period of your time, your phi will be reaching its maximum value. Okay, at the same time, after 3t by 4, so here comes your 3t by 4. At this 3t by 4 time period, your flux will be reaching negative max, minus phi m. Okay, so this is what determines the alternating nature. Okay, why we are saying as an alternating current means so this is the basic reason. Okay, within one period of cycle, your quantity, either it can be flux or either it can be voltage, so it reaches the positive maximum as well as it reaches your negative maximum. Okay, so that's what here they have given. Okay, so here the average rate of change of flux, first you have to get with the average rate of change of flux. The average rate of change of flux means on an average for a particular cycle. Okay, on an average for a particular cycle, so this contributes to a single cycle. On an average for a particular cycle, what will be the average rate of change of your flux? Okay, that's what it deals with. So your flux will be changing for t by 4 time period. Okay, so this can be written as 1 by 4 times of your f. Y means your t equal to 1 by f. Okay, so that's the relation we are applying over here. This t is replaced by your 1 by f, that is time period is equal to reciprocal of your frequency. Okay, so through this the average rate of flux you can easily find. Okay, so phi m will be there followed by the change in flux time period. So that's what will be coming here. So with respect to this, your average rate of change of flux is maximum flux divided by the time at which it changes. Okay, so here the unit is very important. The unit is Weber. So moving to this, so the RMS value of the EMF induced. Okay, so the RMS value of EMF induced. So for this, actually, first you have to get through here. Okay, so it goes like this from this side to this side. So I have made a mistake over here. Okay, so first we will be seeing from here. So now we will be assuming for a singleton. For singleton means, okay, for singleton means for this particular singleton. So this alone turn we will be assuming. Okay, and we will be finding your maximum EMF. Okay, for that particular singleton, we will be applying your Faraday's laws of electromagnetic induction. Okay, so if you are applying a Faraday's laws of electromagnetic induction means you'll be getting the formula like this. So the EMF induced will be equal to 4 times of your operating frequency into your maximum flux. So this is what we have learned from your Faraday's law. Okay, so after this we have to multiply this value with the form factor. So here the form factor is nothing but the RMS value by average value. So RMS value is nothing but your root mean square value. So RMS means it is root mean square value. Okay. So if you are dividing by a root mean square and average value, you will be getting a constant value as 1.11. Why we are doing this means in order to what you can say. So why we will be doing this means for what you can say. This form factor is the one through which your transmission. Uh, so for electrical students, it will be easy to understand because all your transmission lines and all will be rated for 11 kV, 33 kV, 66 kV, like that. So it is mainly due to this form factor. Okay, so it is like an constant number, but it will be having a very significant effect in your transmission system. Okay, so you just see, you just Google about this form factor if you want to know more about it. Okay, so now I'll be continuing with the derivation. So what we need is we need this RMS value. Okay, so you have to multiply this form factor into your average value. So this is your average value. So we'll be applying over here and you will be multiplying with your form factor. Okay, we'll be multiplying with your form factor. So then what happens is that, so you'll be getting 4.44 F 5M volts. So this is RMS value of your EMF induced for single turn. This is the value for your single turn. Okay. So this will be constant for your primary side as well as your secondary side, but the only difference is that the number of windings will plays a critical part. Okay, so if we are going to find your RMS value of the EMF induced at your primary, means you have to multiply with your N1. At the same time, if you want to find for secondary, means you have to multiply with the N2. Okay, that's the main difference. And you know about this formula, right? So phi equal to BA. So there's a particular formula about it. So it is studied in physics. Okay, so this formula you'll be replacing your phi m. Okay. So similarly, how you got this E1, you will be getting this E2. Okay. So after that, we have got all your parameters. Okay. So we have got all your parameters like V1, I1, okay, E2, E2, E1, everything we have got. Now we have to determine the transformer ratio. So it is very, very important. For all the problems, they'll be asking this. Okay. For an ideal transformer, okay, for an ideal transformer, there will be no load. Okay. So at that time period, your V1 and will be equal to E1, and that is your primary voltage will be equal to this voltage will be equal to this voltage, and this E2 will be equal to V2 in case of your ideal transformer. So if you're considering your ideal transformer, you'll be getting like this: V1 I1 equal to V2 I2. So if you're taking the ratio, means this comes over this side and this comes over this side. So you'll be getting V2 by V1 equal to I1 by I2 equal to, okay, this V2 can be replaced by your E2 as per this equation. Okay. So now if you are equating, means if you are equating this equation and this equation, okay, this is your first equation and this is your second equation. Now if you are equating these two equation, means you will be getting E2 by, because all these terms are all constants, so this one get cancelled out and this one gets cancelled out, so you'll be getting E2 by E1 equal to N2 by N1. So the final transformer ratio is K. It's represented by K. This K value will be equal to E2 by E1 equal to N2 by N1 equal to I1 by I2. Okay. So here this N2 by N1, if it is that is your N2 is greater than your N1, means you can easily say it as a step up transformer. Okay, it belongs to the step up transformer. At the same time, if your N2 is less than N1, means your K value will be less than 1, so it will be step down transformer. So your K will be taking the values from 0 to 1. Okay, your K will be taking the values from 0 to 1. Okay, so this is what with respect to your EMF equation. So in this point is very, very important for your one word. Okay, they'll be asking numerous problems with respect to your k term. Okay, so now we'll be moving on a small problem. So what they have given is they have given n1, n2 they have given. So n1 they have given for 400 turns, n2 they have given for 1000 turns. Okay, so also they have given your e1 value, that is the emf induced at your primary. So they have given your A is nothing but the surface area of your core, surface area of your core. So this surface area is given in terms of your centimeter. So you have to convert this into meter. So what you will be doing, you will be making into 10 power minus 2. But here we are speaking about area. So again, this will be squared up. Okay, y means we are speaking about area. Okay, so here they are given your frequency as 50 hertz. So what they have asked to find is they have asked to find your BM, that is your maximum flux density, and the next one is your EMF induced in the secondary, that is E2. Okay, so for this, what you have to know is you have to first write your EMF equation. So with respect to your primary coil, you have to take it out. So your you'll be having this. So in this, you have to find keep phi m at your left hand side and keep bring all the things at the right hand side, and directly have to substitute the values. Okay, you have to substitute the values. So E1 is 520 volt. Okay, E1 is 520 volt, followed by your F is 50 hertz and N1 is 400. So if you are substituting means you will be getting phi m. So after this, you know the formula that phi m equal to Bm into A. So you have to apply that equation phi m equal to Bm into A. Okay. So from this you need Bm. So what you'll be doing, you have to keep the Bm here and you have to convert this phi m by A. Okay. So this phi m value what we have found out, you have to apply here. So we have found out for milliweber. So you will be putting into 10 power minus 3. So A, what we have found out, you have directly you can put over here. Okay. So you'll be getting 0.975 Weber per meter square. Okay. So now we have found out the value of Bm. Okay. Bm we have found out. So next is that from your k equation. So as per this, your k is E2 by E1 equal to E2 by E1 equal to N2 by N1 equal to k. This is equal to k. So from this k equation, you can get this relation. So in this, you know E1, you know N2, you know N1, you know. So directly you have to apply substitute the values. So you'll be getting the E2 to be 1300 volt. Okay, so this is a small problems like this. They'll be asking numerous 1 marks. Okay, in this pattern. Okay. So next we will be moving to the phasor diagram. Okay, we will be moving to your phasor diagram. So here, first we will be considering for your no load. Okay, so if it is the no load means, so at the secondary side there won't be no connection. It will be open. So if it is open means the current at this point I2 will be 0. I2 will be 0. Okay, because here there is no load. So there won't be any kind of current flow. The current will be only flowing when your circuit is closed. When your circuit is closed, only the possibility of current will be to flow will be high. Okay. So next is that we'll be coming to the phasor. Okay, I have already told how to draw about the phasor. Okay. So here this is at your primary. So the primary, the current flow is a I naught. Why you are calling it as an I naught means it is a no load. So at the secondary it is no load. So the current flow will be only flowing through this primary. So it will be I naught. Okay. So this V1 will be leading than your I naught. Why in the sense means normally transformer is consist of coils. So coils means it is nothing but will be having predominantly your inductance effect. So as per that point of view, your you know that for inductive load your current will be lagging behind your voltage. So this is what it occurs. Your current I naught will be lagging behind this voltage V1. Okay, first you have to draw for V1. Okay, V1 you have to draw. So after that you have to go for your I naught. Okay, so I naught. So this will be your IC. Okay, and this will be your IM. So I'll be explaining about IC and IM while taking your equivalent circuit of your transformer. Okay, so now you just see through this V1 and I naught. Okay, so these and all coming under your induced EMF. This will be your E2 followed by your E1. Okay, so the difference between your flux and your E2 and E1 will be 90 degree. Okay, so this is the main thing in your no load condition. Next you will be moving for your on load. Okay, so in the on load, when there is no voltage drop, okay, that is when the voltage drop is not there. Voltage drop is not there means the what is the voltage you are getting across this winding will be at this load. Okay, because these two are in parallel. Okay, so if there is any kind of load at the series in series, then what happens? There will be some kind of voltage drop. So this is what the phase are. Okay, this is what the phase are. So here you can see uh, again your V1 will be there, your I naught will be lagging behind your V1, and after this here you can see there will be the rise of I2. So the I2 parameter will be coming into play. So this I2 will be lagging behind your V2, right? Because again your secondary side will be similar to that of your inductor. Okay, so it will be like this. So after this you have to extend this I2 to I2 dash in order to get your resultant I1. Okay, so next is about on load. So this is how it looks like. Okay, so these are nothing but your this dotted lines are nothing but your flux linkage. So due to the electrical flowing through the primary, okay, the flux will be induced at the secondary. Okay, so because of that only your EMF is formed. So this is for your unity power factor, the phasor for your unity power factor. So here you can see this is for your lagging power factor. So you don't need to get confused with all these things. You have to see with respect to the I naught. Okay, your I naught is what your main thing. I naught and I2. Okay, because the secondary only your primary your current will be flowing. Okay, so here you can see this is with respect to the lagging power factor. So your load will be inductive load, and for the unitive power factor your load will be your load will be resistive load. So here you can see in case of your unity power factor, your voltage and current will be in phase. So this is the main thing you have to take as an outcome through this phasor diagram. All these things and all will be the same. This will be the same. This will be the same. Okay, but this is the main difference occurs. Okay, so this is for resistive load. So here you can see for the inductive load, so your V2 will be there. Okay. So here there will be voltage drop. Due to the voltage drop only, this displacement occurs. Okay. But at this point of view, you will be considering your E2 equal to V2. Why means there won't be any kind of voltage drop. But when the voltage drop occurs, there will be particularly this displacement will be happening. This is what will be occurring in your practical condition of your transformer. Okay. So, if your thing means this V2 will be displaced to a particular angle from your E2. After that, this I2 will be particularly displaced by phi 2 angle. Okay. So, this value will be greater. As it is here, you can see the displaced value will be increasing over here. So, your I1 displacement will also increasing. Okay. So, like this through a like this through your phasor diagram, you can easily find your values, displacement values. Okay. So, next is coming to your leading power factor. So, here in the leading power factor, your load will be capacitive load. So, here you can see your current will be leading your voltage. So, it is very predominantly it is clear that your voltage will be lagging behind your current. This is for your capacitive load. Okay. So based, so all other things and all will be more or less the same. The only difference will be coming for your I2 and your I0. So based upon this, your I0 value will be increasing or decreasing. Okay. So at the next topic, we'll be discussing about equivalent circuit of the transformer. Okay, equivalent circuit of the transformer